All right, good morning, everyone. So I have to say, since as a Carnegie Princeton Fellow, I've visited Princeton several times in the last few years. And the first time I came, very soon after I became a postdoc, David Spergel, he denies remembering this conversation, drove me up to IAS and gave me pointers on what is a good talk. So he's going to give me a grade at the end of this talk. So we'll see how that goes. We'll see what I've learned. Okay. Okay, so today I'm going to be telling you about time domain astronomy. And this is a rather easy talk to give right now because in the last few years, there really has been an advent of wide field imaging. And celestial cinematography, so to speak, has taken off has made an order of magnitude improvement than anything we could have imagined before. So this is primarily, a technical advance where you have CCDs that are affordable, so you can make wide field cameras, and there's several such cameras that have come online. But there are also many amateur eyes in the sky and very fancy robotic telescopes that people have in their backyard making some fun discoveries. So the combination has really transformed our picture of transient astronomy. While this venerable field of discovering novae and supernovae is centuries old, the first supernova was found back in AD 185. It's the 2000s that I think have led to a complete renaissance in this field with many, many new classes of transients discovered. So this movie that you see here was a movie of the Palomar Transient Factory, Pointings on the Sky. So this is the northern sky accessible from Palomar. You saw the clock ticking on the right there from 2009 to 2014. And the color coding here is the number of images at any given point in the sky. So you can see we've covered most of the northern sky hundreds of times just in a few years. Now imagine this whole movie running a factor of 15 faster, and that is going to be the next generation Zwicky Transient Facility that I'll tell you about in that will come online January 2017. And then imagine this whole movie going much deeper, and that's going to be the Large Synoptic Survey telescope that I know several people in this room are excited about for next decade. Okay, so what is the Palomar Transient Factory? The movie that I showed you is step one. It is using a wide field image, taking images of thousands of square degrees, multiple times a night, night after night. But that's just the discovery. The Palomar Transient Factory, the essence of it is in the fact that it's a factory of telescopes churning out transients. So it's a dedicated wide-angle survey which is start to finish. Not only do we discover transients with robotic telescopes, we have inbuilt into the Palomar Transient Factory system a lot of classification and follow-up. So we discover with one telescope, go get light curves with another, set of telescope spectra with another set, UV, X-ray, broadband information, because what excites us about the transient discoveries is the astrophysics. So there is a lot of end-to-end planning that's gone into this project. So what I show here are the pictures of the 48-inch, which is our discovery machine, and the 60-inch, which is also a fully robotic telescope, which is our classification engine. Currently on the Palomar 60-inch, Nick Conadaris is the PI of an instrument called the SED machine. So this is a 30 arc second by 30 arc second IFU, an integral field unit spectrograph, which is point and shoot. So since it's a robotic telescope, it just goes, as soon as the 48-inch discovers a transient, the 60-inch goes to that position and gets an R of 100, very low resolution spectrum, so we can figure out what is it that we've just found. Once these two telescopes have done their work, then there's a slew of other telescopes on various mountaintops. As a Carnegie Princeton Fellow, my favorites have been Las Campanas, and some of you will recognize this beautiful observatory here, Apache Point, at least for the next quarter. And okay, but the total count that the consortium of spectroscopy follow-up that the consortium has put in has been stupendous. It's been 550 nights of spectroscopy on 3 to 5 meter class telescopes in 4.5 years. And this really is the bottleneck and the gold currency behind a successful transient survey. So the Palomar Transient Factory ran from 2009 to 2012, December 2012. And what the phase in which we are running the project now is called IPTF. So I stands for Intermediate Palomar Transient Factory. No, we don't. We're not crazy about Apple and Macintosh. No, it's a joke. Okay. So and IPTF is going to run from 2013 to 2016, and then we transition to the next generation Zwicky Transient Facility. So what is IPTF? We have exactly the same hardware. Palomar 60-inch, Palomar 48-inch at the heart of the system. We have a new collaboration, a new international collaboration. Here's a picture from our summer school last year. But what's fundamentally changed about IPTF is that we have 3 years of PTF experience to build on. So we rewrote the entire real-time pipeline. So PTF, I mean, so I don't know if Robert Lupton is here. If I can't convince you, he'll convince you that software is the backbone of any such project, okay? And what fundamentally distinguishes PTF from IPTF from PTF is the software. Okay, so if I don't convince you, you can talk to him. But a young graduate student, Icha, when I sat down in January 2013, we rewrote the entire pipeline of PTF. And what this has enabled is that we are able to discover transients and follow them up faster than ever before. So here's an example of a random transient that we found, and you can see the x-axis here is in hours after discovery. And within hours after discovery, we are able to discover a transient, confirm it, have an automated, completely automated software, SMS our phone saying, here's a new transient. This is something you want to wake up for. You really should not be asleep at 2 a.m. Okay, that's also just a joke. And then we have a third epoch confirmation of whether this transient is rising or fading. This is something that we hadn't detected the night before. So we knew this was a supernova that was less than 24 hours old. I have a large program on the Gemini telescope, which thankfully is in Hawaii, 3 hours west. So we have a little bit more time before the sun rises on the transient there. So we immediately get spectroscopic follow-up. And then we trigger UV and X-ray follow-up with the program that I have on the Swift telescope. And then we are collaborating with LCO-GT to get continuous coverage on the light curve in this very, very early phase, and radio observations using CARMAT, Avans Valley, and JVLA in Socorro, New Mexico. Okay, so I know this room is mostly theorists, and I'm just showing off my toys before I tell you why this matters and what is the science that this frenzy of excitement at 2 a.m. Leads us to. But I just wanted to give you the backdrop of the science that we are discovering now. So let's say, what is the scorecard of PTF, IPTF? What have we been up to? What have we actually found? So there are two metrics that can be used here. The first is, what is the total number of transients we've discovered? So that is well over 2,275 transients that we've not only discovered but spectroscopically classified. It's a magnitude limited survey. In 60 seconds, we go down to 21st bank, so we can get a spectrum of everything we find. And 2/3 are type 1a supernovae, no surprise there. About 29% or so are core collapse supernovae, which come in 2 different flavors here. And a tiny fraction of the pie, 3%, are transients, which look nothing like supernovae in the literature and nothing like novae in the literature. So these are what I'm going to be concentrating on. I'm sorry, there was a question here? It
looks like a small object.
Yeah, or the 4% is all that matters. Okay, but today I'm going to really be talking about this little tiny slice of the pie where we've got the most amount of observational follow-up with the most number of telescopes, but these are our mysteries, which we don't understand. Of course, I cannot do justice to all the science that PTF and IPTF has been doing because there aren't enough minutes in the talk as a number of things we are finding, but I'll just give you a flavor. So what is this next generation? What after PTF and IPTF? I just want to give you a flavor of that before going into the science. So the Zwicky Transient Facility, which is ZTF, is this camera which is going to live again on the Palomar 48-inch telescope, which is a Schmidt telescope. So you may recall this is the telescope where the past surveys happened with photographic plates, and photographic plates were that big. So right now we populate this tiny fraction of the focal plane with our big 7 square degree camera. What we are doing with ZTF is paving the entire focal plane with brand new silicon that has just become affordable using E2V 6K by 6K detectors. So we'll have silicon the size of a photographic plate and a snapshot field of view of 47 square degrees. This is incredible because if you look on the mountaintop and you have a 47 square degree camera here, that gives you a survey speed of 3,750 square degrees an hour. This is 15 times faster aerial rate and 12 times faster volumetric rate than any survey on the ground today. So just to give you an idea of event rates, I mean that's a metric that some of you may be familiar with LSST. When you're just going and imaging such huge areas of sky, current generation surveys like PTF find of the order of 10 to the 4 events per night. So 10 to the 4 things that varied by more than 5 sigma in space or time, space or flux. Okay? With something like ZTF with this 3,750 square degree per hour, you'd run out of sky in 4 to 5 hours. That's how fast this is. Okay? So you can really image the sky multiple times, the entire accessible sky multiple times a night, night after night. The event rate with something like this would be a few times 10 to the 5 events per night. With LSST, it's a smaller camera, but it's a deeper camera. It's a 10 square degree camera, but on a 6.5 meter telescope. The event rate would be a few times 10 to the 6 events per night. So if you're thinking about large data sets and how to discover a few kilobytes of information in giant petabytes of data, then ZTF would be 1 order of magnitude more than current generation surveys, and 1 order of magnitude on the way to the fire hose of the LSST data stream that I hear the basement of Peyton is being pulled apart for. Okay, so on to the science. Without further ado, the science that I want to tell you about is new classes of transients. So transients can be characterized by 2 very simple properties. This is the Zwicky diagram from the 50s where you put things into morphological boxes in a phase space. On the y-axis here, I have peak luminosity in absolute V magnitude, also in ergs per second. I know there are physicists in the room who don't like absolute magnitude. And on the x-axis, I have time scale. So the characteristic time scale of the transient, again on a log scale, 1 day, 10 days to 100 days. So when I went to grad school in 2005, this picture was very simple. There were novae, classical novae, which are thermonuclear runaways on the surfaces of white dwarfs, type 1a supernovae, which are extremely useful for cosmology, detonations of white dwarfs completely, and core collapse supernovae, which are deaths of massive stars. So the picture was very, very simple. In the last few years, just in the last decade, so this is in 2011, and let me just jump right to 2014. This is what the picture looks like today. This so-called gap between novae and supernovae is long bridged, and it's bridged not just by 1 or 2 classes of new explosions, but several new classes. And this is what I mean by the renaissance in this field. The advent of wide field imaging is helping us find very rare classes of transients with fundamentally different astrophysics than that of the canonical novae and supernovae that we've known about for a long time. So just to give you a sense of rates, novae are 20 per year per galaxy. Hence, we have thousands of them that we know about, but just by looking at a handful of galaxies. Supernovae, 1 per century per galaxy. Most of these circles here have event rates of 1 per 1,000 years per galaxy. So they're rarer than supernovae by at least an order of magnitude. And I think the unexplored phase space here is now going to be the next order of magnitude in rarity, which is 1 per 10,000 years per galaxy. So I can't tell you about all the different pieces of the diagram here, but just suffice to say that they come from various different combinations of compact binary explosions. So I'm sure people here are used to diagrams like this, where 2 stars start off in a particular configuration, and depending on exactly how they evolve, you can get very different types of explosions. So nature is way more creative and can produce a very diverse set of explosions depending on exactly what trajectory the stars followed and what kind of mass transfer happened or didn't happen. But to convert that into a cartoon version of the diagram, the compact binary explosions that we understand the best are carbon-oxygen white dwarf detonations, and those are type 1a supernovae. And these type 1a supernovae could either be double degenerate, so have another white dwarf as a companion, or single degenerate, have some sort of a red supergiant or even a main sequence star as a companion. And I'll show you in a minute that we actually have evidence for both. But there are many other types of compact objects out there. You could imagine that you have a much smaller 0.1, 0.2 solar mass helium white dwarf transferring material to a larger 0.6 solar mass carbon-oxygen white dwarf. And this could give you a wimpy version of a type 1a explosion, which is only about 1/10 as bright. And this is something that on the previous diagram is one of the bubbles in the circle there that we have found. These are 0.1a explosions originally predicted by Lars Bilston at KITP. There are supposed to be neutron-star mergers or neutron-star black hole mergers that we don't really have an example of. We haven't really found yet. I mean, there's some debatable cases, but I would say we don't really have an example of yet because these are much rarer. And then you can take any combination of white dwarf, neutron star, and black hole and try and explain some of these explosions that we are finding. This is where the observers are ahead of the theorists. We find it and then we present to you the puzzle and then we try and figure out what exactly exploded. So I'll give you an example of one such mystery in a bit as well. So I promised to say why I think type 1a supernovae come from both the single degenerate and double degenerate channel. And I promised to convince you why this early time data is very important. So let me give you two examples of type 1a supernovae. That's 2/3 of what we find. But catching them young is extremely important. So in the case of this one type 1a supernova that we found in M101 in 2011, PTF 11 KLY, we found it 11 hours after explosion. So we had the explosion time precisely down to 20 minutes. And if you look at the light curve of this event as the Earth rotated from different countries, that initial light curve can actually tell you that the radius of the thing that exploded was 0.02 our sun. So this is the first direct evidence that we have that the star that got disrupted was a carbon-oxygen white dwarf. Since then, a lot of detailed studies has been done to try and understand what type of progenitor system was this perfectly cosmologically suitable type 1a supernova. It's a very, very standard candle, nothing peculiar about it. But the progenitor system, at least red supergiants were convincingly ruled out. Main sequence stars could still be the case, but most of the evidence actually pointed towards a double degenerate. Yes, this one, yes. So if you have a bigger sample and enough rates, you could do this put even tighter constraints. Recently, just in 2014, this is the PhD thesis of graduate student Yi Chao. We found a type 1a supernova, again, very shortly after explosion, and we got some UV data. So with the case of most type 1a supernovae, which are shown in gray here, you see the UV light curve rise with the optical, as it's a fraction of the bolometric light, nothing too fancy happening there. But in the case of this particular supernova, IPTF 1480G, we found that the UV light curve declined and then rose. And it was much brighter in the UV filters of the Swift satellite than anything else we've seen before. And what we think we are seeing here for the first time, and probably one of the only things that can explain an early decline in the light curve followed by a rise in the ultraviolet wave bands, is that this is a type 1a supernova that's interacting with its single degenerate companion. So you have a 50 solar radius companion that the shock is actually running into. That interaction is very short-lived, and there are some theoretical papers by Dan Kaysen and others that predicted that if that was the case, then you should see an early UV excess, and that before the supernova light dominates.
Did you see anything even harder in the X-rays?
No X-rays at all. So the only thing we have is UV detections. Yeah.
Is there any other evidence for running into an envelope?
So right now the supernova has just gone behind the sun, but Adam Burrows told me the first thing I have to do when it comes back is get a nebulous spectrum, There's a paper from 2000 which says we should CH alpha. So, so we have to just wait for the supernova to come back before before we're able to get a nebula spectrum. But we have seen other examples of type 1e supernovae with a lot of evidence of circumstellar interaction, emission lines in H alpha, calcium, H and K, and so on and so forth. I'm just giving you 2 examples where the early data is diagnostic of the progenitor channels. Now, this particular supernova is not a normal type 1a supernova. It's one of these slow speed supernovae that Chris White here can tell you more about. He's a graduate student at Princeton who came and spent a summer at Carnegie working with me on this project. So what he found was that there are 2 types. So his job was to look through the PTF treasure trove of spectra and see what there is in terms of kinematically low velocity supernovae that were hydrogen poor. And what he identified was that there were 2 such classes. And these 2 classes had very different properties. One had hosts that were blue, one had hosts that were red. One was did not have any signature for cold titanium trough, which is a spectroscopic signature that we often look for in type 1As that are cooler, like 91Bg, like subluminous type 1As. Photometrically, this one rose slower and this one rose faster, which again translates into larger ejector masses and much wider range of luminosities than this one. But the most important thing in this paper is the table 7, which compares the properties of these 2 channels. There isn't a solution as to what exactly these outliers on the Phillips relation and these ill-behaved type 1e supernovae are. But it seems like there's not one answer there. There's two channels to explain what these are. It has been theorized that these could be white dwarf deflagrations instead of detonations. But there are lots of issues with various theories out there to tie this together. And there's one example where for the first time we've seen a UV decline and then rise of a single degenerate progenitor is actually an O2ES-like. So one of the transients that belongs to this category. So it's a very atypical type 1a supernova as well. Slow speeds, it doesn't obey the Phillips relation, so it's not good for cosmology. I mean, in every other spectroscopic respect, it's a 1A, except for the kinematics and this, the fact that it's an outlier on the Phillips relation.
So in which other aspect is a 1A?
Just spectroscopic similarity, it's hydrogen poor, the silicon lines, sulfur lines. Huh?
Does sky bias similarity of spectrum in some aspects?
Yeah, in some aspects, so. But
was it a star-forming galaxy?
No, this was an S0 galaxy. So an oldish galaxy. Okay, but now to my favorite piece of the, I'm sorry? Shock breakout from a type 1A. I would imagine the time scales. Yeah, we do have X-ray because Swift observes in X-ray and UV simultaneously, and there is nothing in the X-ray. And I would imagine the time scales for shock breakout in such compact objects would be much smaller than what we see. We see a few days of a decline and then a rise. Yeah, it's not hours there. So, so I would say that is unlikely. Okay, now let me talk about one of these classes of transients that have been bothering me for a few years, which are these calcium-rich gap transients. So this is a big sample of 8 rare transients that we found. So let me give you some background. These are gap transients because if you look at the light curve, so this is luminosity as a function of time. These transients are fainter than your normal type 1e supernova by a few magnitudes, and they evolve relatively faster. There's not much of a range. I mean, the range here in absolute magnitudes is not very large. And there's now a sample of 8 of these just in the last few years. Spectroscopically, they are very different from supernovae. And in particular, if you look at nebular spectra, that's when you actually see what the ejector is directly composed of, because you've waited for several months to a year usually for the ejector to become optically thin, and you can now directly look at the composition of the ejector. So in the case of core collapse supernovae, which are the first 3 year, you usually see several solar masses of hydrogen, oxygen, calcium, because it's a massive star that just died. In the case of a type 1a supernova, you see iron 3, cobalt 3 lines, signatures of radioactivity, which powered the explosion. In black here, you see the sample of calcium-rich gap transients. And as the name suggests, these things are extremely calcium-rich. By far, the strongest line is calcium. I showed you the light curve, which has a low luminosity and a relatively faster rise. This means that the total amount of ejecta is very small. The total amount of ejecta is only half a solar mass or so. But most of that ejecta is surprisingly calcium. So if the ejecta mass is about 0.5 solar masses, about 0.14 solar masses or so is calcium. So to summarize these 5 properties, you have the 2 that come from the photometry, which is lower peak luminosity, faster rise and decline. Photospheric velocities are explosive, 10,000 kilometers per second. In just 3 months, you get a nebular spectrum, and this nebular spectrum is dominated by calcium. So 5 very basic properties. Now, if you look for all types of transients in archival data, however, with a fine-tooth comb and look for everything that satisfies these first 5 properties, there's a 6th property which is actually the hardest to explain, which is the locations of these transients. So systematically, again and again and again, whenever we found these transients, they've been very, very far away from their host galaxies. So for example, this transient here is 40 kiloparsec away from its host galaxy. This one is 37, this one is 33 kiloparsec. So there's basically the distance between the transient and the host galaxy, the same redshift, is somewhere between 20 and 40 kiloparsec. If you wait for the transient to fade and go and get deep imaging at this location, and there's a nice paper by Lyman et al. Using VLT and going all the way down to -6 absolute magnitude. So this is where you can start resolving globular clusters at these distances. There's just nothing there. So it's not a dwarf satellite galaxy that we just don't see in the data. There really is nothing there. In some cases, it's not just one galaxy that it is in. It seems like it's an intra-group medium, and in one case, an intra-cluster medium. So this is a transient in a cluster I hope at least some people recognize. This is the Coma cluster, one of the densest and richest galaxy clusters out there. In this case, a transient had many galaxies to choose from. Yet the closest galaxy to this transient, which is at the same redshift as the Coma cluster, was 30 kiloparsec away. This whole issue with offsets is not a red herring. The first time we found it, we were very puzzled. But it seems to be actually an important clue into the origin of these events.
How accurately is it the same redshift?
Extremely accurately. I mean, supernova lines are broad. So, I think there might be some dispersion of a few hundred kilometers per second just because of the fact that the lines are broad. But the dispersion is not, for example, in the intra-cluster medium ones, the dispersion in the cluster and the group is much larger than the dispersion between the velocity of the supernova and the putative host. So when I found the first few of these, I presented it at Wunsch, Princeton Wunsch. And at that time, I just left the slide at this thing. I have no idea what these things are, and we need to figure out an answer. So at that time, Tim was a graduate student at Princeton, and he came to my office and he said, okay, let's work out how much do these things need to be kicked by to actually explain this, okay? And the Brian Metzger was a postdoc, an Einstein fellow at Princeton. And basically, I think now, at least based on papers, based on a recent paper that just came out this summer, that this idea of kicking things out of the host galaxies might actually work. It definitely doesn't work for massive stars because massive stars have way too short a lifetime. But if you have a multiple star system, of which one goes off as a supernova, and you eject a white dwarf neutron star pair and set it off with a few hundred kilometers per second kick off into the middle of nowhere, then after a long time, at some point, the white dwarf could start getting tidally disrupted by the neutron star. And in that situation, you could plausibly explain these events. And so in this paper by Church et al., he looks at population synthesis of white dwarf neutron star systems and finds that this weird offset distribution is actually consistent with what we find. So we finally, I think, can try and fill in those missing circles of what is going on here. But there are details which are still puzzling. You produce some calcium when you disrupt a white dwarf into a neutron star, but whether you get exactly so much calcium as we observe is still not clear. So Brian wrote this paper in 2012 which looked at nuclear-dominated accretion outflows, where he looked at the chemistry of what this would do, and it's possible to generate some calcium, but how do you get the explosive nucleosynthesis to stop at calcium? I don't think we know the answer to that yet.
So these are fainter than normal 1As.
Mhm.
Would you have seen them if they were still in the host galaxy?
Absolutely. So the first time we found it, we were a bit panicked. I mean, are we missing things that are in just because of the host galaxy confusing us? But we found many events which are much fainter, much faster evolving, and in much brighter hosts. So it's not a selection effect.
So you're saying these things only happen to things which have been kicked out?
Yes. This sort of peculiar calcium-rich signature, I mean, at least predominantly. I mean, now we have a sample of 8, which is what we're working with. But so predominantly, it is the case. There might be a smaller subset that somehow get kicked, but don't quite escape, and we could happen a bit closer. But
if it is the white dwarf neutron star, then it says something about their initial separation. That's canonical. In order for them to have the tidal disruption, right?
right. So
How big is it?
I don't know the numbers off the top of my head, but I think it'll be a function of exactly what the configuration of that system was. And not all the ones that get ejected will actually end up like this as well.
Why is the kick essential to getting the spectrum? I mean, if this mechanism worked, a white dwarf neutron star binary that's not sitting in a three-body system, you think would produce the same spectrum?
If the mechanism always produced a kick to form them, then and their separation was such that the time scale required for them to disrupt, then you would have the correspondence between the two. Just a time.
Right, but you need somehow the mechanism that the kicking is vital to the emission.
Right, so the dynamics of the system have to somehow be tied in, and I don't think we understand exactly what distribution of orbital separations and kick velocities will give you a system that will tidally disrupt and what fraction would. But so it's just I mean, there's a question mark at the end, okay, because I think the details do need to be figured out on this. But it's at least an idea that sort of fits the clues. I mean, several other ideas were proposed which really struggle with this fact that these things happen where there are no stars and there's no light and there's no mass. So it's just too far out in the outskirts of galaxies. I mean, there was a proposal that these happen in globular clusters, for instance, but there's no globular cluster there. So that's kind of tough.
How much nickel is proposed?
The total ejector mass is 0.4 to 0.6 solar masses. Nickel is, I think, less than 0.1 of that. There's only a limit on that, just based on the light curve, assuming that because you could have the light curve powered by nickel 56, but you could have the light curve powered by other radioactive species like titanium 44 and decaying into titanium 44 to calcium 44, etc. So you could have a I'm sorry.
The decay time of the titanium is too long to explain. What is the life of the transit?
Several days, 10 days or so. So no, there's a paper actually I would refer you to where they look at a combination of different radioactive species as a better fit to the light curve as opposed to just nickel 56 alone. But if you say just nickel 56 alone, it's about less than, it's of the order of 0.1 solar masses or so, not much more than that. So, okay, but regardless of the origin, there's one thing that's clear about this class of events is that they are responsible for about half the calcium in the universe. So this here is a summary. This is a puzzle that X-ray astronomers mused over for several years, and John Mulcahy is an X-ray astronomer at Carnegie who told me about this. So this is a review paper by Dipla from 2007, where you look at intra-cluster medium abundance measurements. So this is abundance ratios is relative to iron. These error points with error bars are the X-ray measurements, and these dotted lines are fits of how much of each element could be explained by type 1a supernovae and core collapse supernovae, and the solid line is the sum. So as you can see from this 2007 paper, this is not a very good fit at all. The chi-square here is 84 because one element sticks out like a sore thumb. And what John and I worked out on the back of an envelope when he came back from this X-ray meeting was if you add in these calcium-rich gap transients, although they're very, very rare, they produce so much calcium per event, and potentially this calcium is more easily mixed into the ICM because of their locations, that they can very neatly explain the missing calcium in the ICM. So independent of the origin, I think there is this class of rare transients cannot be ignored.
They always found in the ICM? Or are
Um,
they found sometimes just in isolated galaxies, kicked out of isolated?
So we have 1 in a rich cluster in coma. We have 3 in some sort of a group of sparse group of galaxies, and then the remaining are in some sort of loose group with only 2 or 3 members. So if you look out to a megaparsec, you find a couple of other galaxies which are consistent. So very sparse. There's only 1 in a very rich cluster. There's none that is truly isolated with no other galaxy even out to a projected offset of 1 megaparsec. So there's some more details here which I will skip.
So will any of that calcium make it in the stars?
Sure.
Okay.
Huh?
I mean, you're creating the calcium
Yeah.
50 kiloparsecs out.
Uh-huh.
So it's actually, you may have had that on the plots you went over, just points, but measurements of the calcium to iron ratio within galaxies and within clusters should then be really quite interesting tracers of what's going on with the intergalactic medium. Because all the iron's being created inside and the calcium's being created out there.
Right.
And you expect a calcium to iron gradient. And
Yep.
by measuring how much calcium flows back in, we can get a measurement of how much infall there is from the hot halo.
Absolutely. So if you can spatially resolve these types of measurements, that would be fantastic.
But I would have thought
And what has
contra observations of calcium lines and iron,
right now they treat the entire, these papers have treated the entire cluster as a pixel and just summed up the abundances there. So I've not seen any examples of some spatially resolved work, but Charlie Conroy has this paper which shows that calcium tracks iron and not oxygen, which is consistent with this argument.
That's radio, but you would
Yeah.
actually expect that calcium is just further out than anything else. I mean, this
Yeah.
says calcium is being created at different sites physically
Yeah.
than anything else.
If you can spatially map that, I think that would be an excellent test of that.
Resolved X-ray measurements for metallicities from the center out, but I don't know how the calcium to iron ratio depends, but there are observations that
Okay.
can probably show that.
Yeah, my sense was that there isn't that spatial resolution yet in these distant in these distant clusters where this has been measured.
Take Andromeda
But-
and look at the calcium to iron versus radius in Andromeda.
Yeah, but that's a pretty big galaxy, right? So struggle. And a big field of view with an X-ray telescope, which we don't have yet.
Well, but you match it to your resolution, X and M, whatever is what you want with spectral resolution, choose the right size.
I think they have it for clusters, but I don't know what the effect is.
You say you can rule out globulus. Can you rule out dwarf, very faint dwarfs?
Yeah, so dwarfs fainter than -6 absolute magnitude. Yeah, so that these ultra compact dwarf galaxies, which right. So actually we have some. So for the I don't have a surface brightness limit for you because that's actually better done with HST, and I have an HST program which is going to go and image these locations, and then I can give you a better surface brightness limit than just a point source limiting magnitude limit. Right. So. But something about the environment and location is a clue here. So,
What are the units on the y-axis?
okay, these are X-ray astronomer units. I don't. Okay, this is the abundance ratio relative to iron. So iron is defined
Just
as
the
1,
number of atoms?
and so you can again. I refuted the paper to look at the details, but the way they do it is a logarithmic ratio relative to solar. So you have to actually look at the abundances with solar elements and convert it. But this is number. So these lines are numbers. So you can literally think of it as a number of atoms. So there are two things, right? Either you need to produce more calcium per event, or
This number that you plotted for this calcium explosion,
Mhm.
this 0.4, what does it mean? For every
means
atom of iron, I get how much calcium?
Is that a log scale or a linear scale?
this is a ratio of 2 logs. So it's a ratio. So it's calcium over. Okay, sorry. This is a really bad convention, right? So it's relative to iron, and then it's ratio of relative to the sun. Okay, so it's calcium over iron, and then that's why they use these square brackets, but in any case. But basically, I mean, the way for you to think about this is that this translates to the fraction of calcium that's produced by each of these. So there are two things, right? Either you could have more.
So the observation should be one.
I'm sorry?
So the measure shouldn't be just one.
No, because it's relative to iron. The one is iron, the abundance of iron.
But is it normalized by what we observe in the sun? So
Each element is individually normalized by the, I think we're getting into details here. So I refer you to the paper, and I promise you the equations in the paper that you can work through. Okay, no, let's not worry about that. Okay, at this stage. So let's keep going here. So now you can see I've taken the same diagram that I showed you before with luminosity and time scale and scooshed everything that I really care about to the right. Because what we are opening up now with experiments from IPTF and definitely in a big way with the Zwicky Transient Factory is transients on timescales shorter than 1 day. So there's a new gap or a new unexplored region of phase space in Zwicky's diagram. And one of the things that lives here are neutron-star mergers. So I assume that people are familiar with neutron-star black hole mergers. So I'll try to breeze through this a little quickly. But this to me is an exciting new frontier in the next phase of transients that are fainter, faster, and rarer than what we have been able to find today. So this is the motivation for the title of the talk. So when you have neutron-star mergers or neutron-star black hole mergers, of course the fundamental signature is that these are extreme events in terms of the gravity, and you can use the strong field gravity to detect them using gravitational wave interferometers like advanced LIGO and Virgo. And that gravitational wave signature alone will give you information about the masses, spins, and inclination. So this is a group of 3,000 physicists who've been working really hard for 30-something years, but they're finally getting ready to detect neutron-star mergers as early as next year. Next year is when the interferometers have their first 3-month run in the advanced sensitivity situation. But that is just the sound. All the physicists can do is hear the sound waves, because the frequency of operation of advanced LIGO is between hundreds of hertz to thousands of hertz. It's exactly the same range as a human ear sound. What I care about is actually understanding where these transients happened. So localizations from advanced LIGO will be extremely poor, so thousands of square degrees to hundreds of square degrees to start off with. But to understand the astrophysics, you want to know which galaxy this happened in, at what redshift did it happen in, what are the energetics, what is the environment, what is the chemistry of what happens here. In fact, chemically, these things are supposed to be the sites of our process, nucleosynthesis, and this is where most of the elements in the periodic table that are heavy, about half the elements in the periodic table heavier than iron are supposed to be synthesized. We don't know the answer to that question yet. So there are a couple of electromagnetic signatures that have been predicted, and there's a whole slew of papers on this topic. The first prediction is that some small fraction of neutrons escape. So you have free neutrons, just 2.5% or so that escape, and they decay, and they can power a short-lived blue flash for a few hours to a day. The second prediction is this kilonova prediction, which is that because you have such neutron-rich material, you're synthesizing these heavy elements, and these heavy elements then radioactively decay and give you a redder transient because of opacity that is on the time scale of a few days. So you have a short-lived blue flash and a longer-lived red transient. And of course, some of the elements here, some people might care about more, gold and platinum. That's why there's a cartoon here with a golden halo. Just to make you laugh. Okay. Okay, back to seriousness here. So localizations. So I just explained to you that these are gravitational wave interferometers. So if you have 3 to 5 interferometers, so okay, let's start with the simplest case. If you have 2 interferometers, then you have a ring on the sky. All you have is a 32 millisecond time delay between when the gravitational wave reached the interferometer in Hanford and when it reached in Louisiana. So that gives you a 6-degree wide ring on the sky. If you have 3 to 5 interferometers, you can triangulate and get distributions that are tens to a few square degrees. But in the early years, it's expected that we will only have 2 interferometers that are so sensitive. So you have this awful ring which is 10,000 square degrees to work with. If that was the case, then this would not be a problem worth going after, because 10,000 square degrees is a formidable fraction of the sky, and trying to find something that's spatially and temporally coincident in such a huge area is impossible. But there is one more clue that you can use, and that is the fact that these waveforms are slightly different in other parameters, such as amplitude and phase. And that can be used to break the degeneracy in the ring, and instead of this awful 10,000 square degree ring, you end up with these localization bananas, which have a median localization of 250 square degrees. So that's the first point to take away from this plot, is that it's not so bad even with 2 interferometers. It's 250 square degrees, which is much more palatable than 10,000. The second thing to take away from this plot is that the localization is limited to 2 sky quadrants. So this should be no surprise. You have a quadrupolar antenna pattern for gravitational wave interferometers, which are almost perfectly aligned to maximize sensitivity. But it means that they're only sensitive to things directly above and directly below. So if you're looking for a blue flash of light that only lasts for a few hours, then you don't have the luxury of waiting for the Earth to rotate before that location comes overhead. So you should try and put your telescopes up here or in the Indian Ocean or South Africa. Okay? So that's another important point, very basic concept in doing this search. And using these, you can try and figure out what fraction of kilonova phase space can be probed by various facilities. I won't go into the details here, just suffice to say that even small telescopes with large areas can actually probe a very significant fraction of the phase space, the theoretically predicted phase space of ejector mass, ejector velocities. You don't necessarily need a very big telescope to do this. But there's a bigger challenge here. You've been hearing all about how dynamic the optical transient sky is. So if you go and look in 250 square degrees and get an image, you'll find thousands of transients that have absolutely nothing to do with the gravitational wave event. There'll be several moving objects in the solar system, eruptive things in the Milky Way, background supernovae and AGN that have nothing to do with the neutron submerger that, say, happened in the Virgo cluster here. So how do we address this problem, given that these things will be 20-second mag, or something so faint that you need even bigger glass to try and get a spectrum and to confirm what you found and get some physics and astrophysics and chemistry out of this thing to see if there are heavy elements in this or not? The number of large telescopes is small. They fit on one slide. But the challenge is much worse. So how do we go about finding the needle in the haystack? How well can we find a transient in such a large error box? Can we practice? Can we at least start to develop the software or the backbone to actually do this? So I'm going to tell you about the thesis project of a young graduate student from the physics department at Caltech, Leo Singer, who was brave enough to sign up for this project with me. So what we started to do in preparation for the LIGO challenge is to look for afterglows of Fermi GBM bursts. The only thing the two things have in common is that they're just as poorly localized. So the GBM instrument in Fermi also has a very coarse localization on sky, and you're looking for something that's spatially, temporally, and physically coincident with this event. So this is an example of the first such afterglow we found, which was in this chip at this location. You can see this galaxy group. There was no transient here, and then there was one, the afterglow that we discovered. The way we did this was we went and imaged 70 square degrees in this case and found 27,004 candidates. Before the sun rose, we had to get this down from 27,004 to 26,000 to 4,000 to 2,700 to 43 to 7 to 3 that we got a spectrum of. And one turned out to be the true afterglow. And all we had was a few hours before sunrise to get this right.
What's the human scanner part?
I mean, there is.
Obviously, you look at them, but do you just look at so many of these things, you have a sense of what's interesting that you haven't been able to teach a computer?
Right. So machine learning gets us a long way, but not all the way. There are some things that the human eye can do much better, which is figure out if there's an offset between the transient position and the nucleus of the galaxy, look at the light curve history, cross-correlate with other archives. So we have inbuilt onto this web interface, this dynamic web interface, information about whether there's an X-ray source, radio source, anything from any other catalog that's known about that position. And the simplest way to, is to just look through the small number of candidates by eye to go from which of the 43 are most relevant. So there's a lot of details in how you actually go from 27,004 to 1 in the matter of few hours. But in this case, this first case, we actually had a huge advantage. We sort of had a lucky break because this afterglow was 17th magnitude. So it was extremely bright. What we've done since this is a thesis project is to do this over and over and over again. So we've done this 8 times now, and we found afterglows in such large areas by going and imaging large areas and finding an afterglow with spectroscopic, X-ray, and radio conformation, all the way out to redshift of 3.29. So the faintest afterglow that we've found is now 20th mag. So we've gone from 17th mag to 20th mag in a year. Now we need to get down to 22nd mag to be able to find, to be able to address the LIGO challenge. But preparation is well on its way. We are even finding relativistic explosions independent of high energy triggers. So here's an example of a relativistic explosion where we found the afterglow, and later in this window, after we announced the event, in this window, a weak signal from the interplanetary network was recovered. So in one case, the parents of the canonical orphan afterglow were found. In another case, they're still missing. But I don't think I have time to go into the details of any of that right now. I just want to spend the last few minutes telling you about completely changing gears to the infrared aspect of this game, which is looking for dynamic infrared transients. So unlike the optical, where I've shown you a rich diversity of different types of transients and new classes, and the problem of having tens of thousands of transients and figuring out which one, the infrared has the opposite problem. The infrared sky is completely pristine territory. We simply don't have technology. We don't have, infrared detectors are extremely expensive, and we don't have wide field detectors. The biggest detector that exists right now is a 0.6 square degree detector. After that, it's 0.12, and then everything else is less than 0.1. So there's not even a 1 square degree infrared detector out there. So in that sense, the infrared transient sky is very, very new territory. So what I did was start a project with the Spitzer Space Telescope, which is now in its warm mission with the IRAC camera, and do a targeted search of nearby galaxies. So I had 190 galaxies that Spitzer is looking at multiple times at 3.6 micron and 4.5 micron. I'm simultaneously, not simultaneously, but concomitantly imaging these galaxies from several telescopes on the ground in the optical and the near infrared, and looking for infrared transients. So transients that have emission restricted to the infrared bands. And my motivation here was, again, you can see here, instead of giving you luminosity time scale and 1 point per object, I'm giving you light curves. So novae live down here, supernovae live up here, and there are these intermediate luminosity red transients, which is one of those bubbles in my diagram, which live up here. So there's, just like in the optical, there's a luminosity gap between novae and supernovae in the mid-infrared. And what we found is several transients in between this gap, just by looking. In fact, we found, sorry, that slide needs to be updated. We found 35 infrared transients with no counterpart in archival Spitzer imaging, a bright transient in the images we've taken this year. And these have more or less always happened in grand spirals. We have both spirals and ellipticals in our sample, massive ellipticals, and they've always happened in intense star-forming regions, such as these two examples here. They've been extremely cold, so they've had temperatures between 500 and 3000 Kelvin, and just no optical counterparts to deep limits, either with Keck, and we just got some HST data. There's just nothing there in the optical. So these are extremely cold transients. Let me tell you, in terms of photometric evolution, there's a diversity of fast rise, very slow decline, so flat for several years, slow rise, fast decline details. Let me tell you about one in a little bit more detail here. We got a spectrum with MOSFER, and that's what I have to fly back for tonight. And what we found were these emission lines here, these weak emission lines. you can see there's no continuum, but there's excited molecular hydrogen emission. I'm used to ionized hydrogen, not molecular hydrogen. So this was very surprising that there's H sub 2 emission in these in this transient. These emission lines, this transient occurred in M83 in the position of this red cloud. This is a CO map from the Noboyama millimeter array. So it occurred in a region of intense star formation. So something is driving a shock in this that is exciting these molecular hydrogen lines. So what could be driving a shock that gives you such an extremely red and luminous transient? So there are two ideas. One is that this is the birth of a massive star binary. So you have a cloud collapsing to form massive stars. You have a non-hierarchical system, and you have dynamical capture in an unstable way. And this here is a cartoon of the OMC1 system from Bali et al. 2005. And you can see that when you form the massive star binary, you can have they'll be ejected in different directions. And in the case of the Orion molecular cloud, you can have proper motion vectors that show you that 500 years ago they came from the same spot, and that can tell you that this is what exactly happened to these ejected stars. So in this case, you might be seeing the first extragalactic example of a massive star binary that's being formed, that's driving a shock in the GMC, and we are seeing the consequent hydrogen emission. Except it's only 4 years old, not 500 years old. So we can actually get a complete census of these things if this is indeed the correct interpretation. The second possibility is that this is some sort of a supernova that is either behind the molecular cloud or somehow didn't have strong enough winds to destroy the cloud that it was born in. And I don't think that this is actually relevant because supernovae have very strong stellar winds which destroy the cloud. But I just wanted to point out that the very first paper I wrote was a theory paper full of equations, and it was about confining supernovae in molecular clouds. Okay, just for fun. So I'm going to skip through this because we are out of time and go straight to my summary. So I told you a little bit about new classes of optical transients, gave you a flavor of what we are up to with the Palomar Transient Factory and this new Zwicky Transient Facility that we are super excited about bringing online in January 2017. And thanks to NSF Mid-Scale Innovation Program, this is now fully funded and on course. I told you about some fun I've been having with infrared transients and the beginnings of a systematic survey there. So please stay tuned. And the third, I told you about the challenge or the puzzle that I'm most excited about, that I think we actually might be able to answer in this decade, which is actually seeing the sound associated with neutron-star black hole mergers. So that's it. Thank you very much for your time and attention.